Okay, so time to get started. So we were almost done with 1.2 last time. Here's the last little bit that I needed to get to. We know how to generate points on a line, right? If you have a line in space, here's how you generate points on a line. Point generator, parameterization of a line. In 2 dimensions, we have seen a point tester, namely the equation of the line in 2 dimensions. The only thing is, you can't really talk about the equation of a line in 3 dimensions, because in 3 dimensions, an equation gives you a surface, not a line, right? So what if you want something that plays the role of an equation? What if you want a point tester for a line in R3? What is the test? Not a generator, but a test. And it's going to end up being this thing called the symmetric equations. So let me explain how you turn a parameterization into a tester, into the symmetric equations. I'm going to start with, I guess the first thing I have to do is talk about notation a little bit. This is just annoying, but it's got to get said. This little symbol right here, let me circle it better. There you go. This symbol here means there is or there exists, something to that effect. And then this little symbol right here means so that or such that, depending on the context. So what, this is going to seem like a silly thing to claim as being a test, but technically a sort of a test is, look, if there's some value of t that generates the point you're interested in by way of the parameterization, then yes, that point is on the line. Now, let me complain about what a stinky test this is. How am I supposed to find the t? Right? The t has not been given to me. You just came to me with a point. How do I know whether there's a t that this will generate the point or not? Right? So, not a useful test. You could point out. All right, so how are we going to turn this into something useful? The big idea to keep in mind here is that this is actually 3 equations, right? The first equation is what you get by looking only at the first coordinate. Second equation, second coordinate. Third equation, third coordinate. Each of these equations has t in it. In each of these equations, you can solve for t. And now let's ask the question from this different point of view, keeping in mind that a vector equation is equivalent to the trio of scalar coordinate equations. How would there be a value of t that satisfies all 3 of these equations? Let me say that a little bit differently. How could there be a value of t that's equal to this and this and this? Can there be a value of t that's equal to 3 different things?
They all have to be equal to each other.
That's exactly the point. That's right. So if t needs to equal to 3 things, those 3 things have to equal to each other. That's exactly it. So that is the symmetric equations. These 3 things have to equal to each other so that there can be a value of t equal to all 3 of them. So that this equation will generate the point that we're trying to test. So that's the big idea. So this is called, again, the symmetric equations, and it plays the role of a point tester for a line in R3. Okay, so that was the last little bit we just needed to wrap up. We're going to move on now to dot products 1.3. I will remind you, tough choices, limited contact time. I'm not going to be able to cover everything, etc. You all have seen dot products before. It's used heavily in linear algebra. I think you should know pretty much. I mean, there's a couple of things I'm going to talk about, but I am going to suggest that you should review all of 1.3 just to be sure, right? Just in case. But I'm going to sort of assume that you're good on most of this stuff. So I do want to say a few things, though. This business right here is kind of a personal pet peeve of mine. These 2 words, perpendicular and orthogonal, very often used interchangeably. I think that's at least a missed opportunity. I don't want to say it's wrong, but it's I don't like it. And it's, I think, like I say, I think it's a missed opportunity. And let me explain what I mean by a missed opportunity. Here's the situation as it stands. There's this geometric idea of two vectors pointing in two different directions where those directions are perpendicular, where the angle between those two directions is a right angle. Right? That's all geometric talk. Direction is a geometric idea. An angle is a geometric idea, right? So this geometric idea is one thing, but now here is a closely related but importantly different idea, and that is this idea of a dot product being zero. Now this is purely algebra, right? Dot product is an algebraic operation. Equation, algebra, right? So these are very, very closely related. These are so closely related that a lot of students playing a little too fast and loose with the ideas think they're the same. And they're not. Very importantly, these are different. This geometric idea only makes sense if the vectors actually point in actual directions. Right? So the zero vector, for example, doesn't make any sense in terms of this geometric idea. What direction is the zero vector pointing? It's either pointing in no direction, or in some sense it's pointing in all directions, but we can't make sense out of the idea of perpendicularity at all. There's no such thing as a right angle if zero is responsible for defining one of the directions. Does that make sense? And yet, this algebraic thing, no problem. U is the zero vector? Okay, cool, whatever. Dot product, yeah, compute it away. It's no problem at all. Yeah?
So other than zero, are they the same?
Other than zero, they are the same. That's right. Yeah. So whenever both of the vectors are non-zero vectors, these are, I'll say they're simultaneous. Right? Green always implies blue, and blue always implies green. Now, I'm going to quibble and point out that it does still remain that one of them is geometric and one of them is algebraic. Right? But yes, they are always coincidental when the vectors are non-zero. So here's the situation that we. Oh yeah, question.
So can you not then technically say that if a zero vector and another vector, the dot product equals zero, then they're not perpendicular?
Yeah, technically, if all you know about two vectors is that the dot product is zero, you can't conclude anything about the angle between them because you don't know that there is an angle between them. Yeah, that's the problem. Okay. Does that answer your question?
Yeah, I'm essentially asking, like, can the zero vector be perpendicular?
Nope. My position on that is it just doesn't make any sense because perpendicular suggests that I have two directions defining an angle, and I say the zero vector doesn't define a direction. So yeah, is that satisfying?
Yes.
Okay. So here's our situation. We have two words and we have two, I'm going to say, importantly distinct ideas. Well, then let's use one for one and the other for the other, seems to me, right? And given that the word perpendicular is pretty dyed in the wool, pretty well established, that's referring to the geometric idea we described here, I think it falls that orthogonal should refer to this idea right here. Right? So now this, look, mathematicians won't get too upset about this because they know what they meant, right? And I know that they know what they meant, and they know that I know that they know. This is not really a problem, right? But in a context like this, I think it is actually important to make this distinction because sometimes we will need specifically to be referring to a statement about geometry, and sometimes we will need to specifically be referring to a statement about algebra. And so try to use these words, please, in these senses specifically. And I will do the same. Now, I have a long history of using these ideas before I became very careful about the distinction, and so I'm probably going to mess up here and there. Apologies in advance. Sometimes I will say orthogonal when I meant perpendicular. And sometimes vice versa. But my inability to be perfect on it is not the same as my thinking that it's okay to be imperfect on it. So I hope that makes sense. All right. Okay, moving along. Here's another thing about vectors. Again, I think y'all almost certainly know. But if you have a non-zero vector, that defines a direction. And if you want to know what is the unit vector that points in that direction, which, by the way, we're going to need pretty regularly. Here's the handy-dandy little formula that does it. Any non-zero vector v, if you take that vector and divide it by its own magnitude, will give you this unit vector, pointing in the same direction but with unit magnitude. So it's a handy trick. You're going to find that we'll be using this over and over again. Again, you've probably seen this before, but I think it's worthy of mention just in case. Okay. All right. Here's another thing that I think is worthy of mention, just because this might not have come up in linear algebra class. This idea of a component. Suppose that we have some vector w. It points a certain amount in some direction. But what if I'm interested only in what's happening in another direction? And my favorite metaphor for this is, suppose this is a football field, and I want the ball to go downfield. And, if we need to make 10 yards for the first down, I can't go 10 yards that way, right? It's only the extent to which the ball goes downfield that we actually care about. So if the ball were to start there and end there, how many yards did we gain or lose, possibly lose, right? If you get sacked or whatever, right? Well, whatever's going perpendicular to the green line is irrelevant. It's got nothing to do with yardage gain, right? So what we're actually interested in this situation is this right here. So how much a vector points in a given direction, not in the direction that it points, but how much is it pointing in another given direction is what we call a component. Now, very importantly, sadly, confusingly, do keep in mind it's allowed to be negative. And if this W vector pointed like so, that would be a negative component in the green direction. So you can't call it a distance. And it's very frustrating because it looks like a distance in the picture, right? You also can't call it a magnitude, but you're going to want to call it a magnitude, but you can't. It's not a positive thing necessarily. Magnitude is intrinsically positive. Distance is intrinsically positive. Component's not. Right? So you can call it a scalar. That's fine. Right? But just to be wary of these other words. Okay, so geometrically, are we all comfortable with the idea of what a component looks like per the picture there? Yeah?
It's the same thing as a projection.
Very good question. It is very closely related, but it is a different thing, and I'm going to get to that on the next page. Yeah, totally. Okay, so how are we going to compute a component? And the big idea here is to notice that we have whoopsie, that's not what I meant. We have a right triangle here on which we can do a little trig. Trust you all to be good with the trig. Right? The component that I am interested in is part of that trig, which I can then solve for. And then I'm going to pull a real fast one here. I'm going to take this formula and I'm going to multiply and divide by the same thing, which is perfectly legal, seemingly pointless, but perfectly legal. Okay? And the whole reason that I do that little move is because it allows me to recognize the numerator as being the dot product. Again, flashback to old formulas about dot products. And thus, I get a nice and convenient little formula for how to compute components. And let me simplify. We'll get rid of all that jazz. So here's your formula for computing components. It's V dot W divided by the magnitude of V, namely the magnitude of that direction vector. Everybody good? Bam. Okay, now here's a different way to think about this formula. Same formula. And that is to observe that what we are dotting W with is exactly the unit vector that we referred to at the top of this page. The unit vector pointing in the direction of V. So that's another really nice way to think about it. And frankly, my preferred way to think about components. And I have this summarized in the little pithy little statement down here. Oh gosh, that's not the color I wanted. Well, okay, anyway, this equation and this little pithy phrase, components are dot products with unit vectors. So very, very succinct and to the point, right? I think this is a really nice way to think of. Frankly, this is a really nice way to think about dot products, right? So if you're looking for geometric satisfaction of what is a dot product, what is it? Point to the dot product. Where is it on the screen? Dot products are components when you're taking a dot product with a unit vector. So now there is this little asterisk. It only works for unit vectors. Oh, so does that. But nevertheless, this gives some geometric satisfaction, I think, in making sense out of dot products. Okay. Pausing. Everybody happy? Okay, so projections. What's the deal there? Very, very similar. Also, another topic where, sadly, there's not 100% consistency with how the language is used. Different people use the word projection where other people use the word component. It's very frustrating. We're going to be consistent within this class. I'm going to use the same convention that the book does. And specifically, projection and component look a lot alike. The difference being that while the component is a scalar, the projection is the vector. I mean, same kind of deal. It's the look at the W, yeah, but I only care about the in this direction here. Same basic idea, but component being a scalar, the projection is a vector. Everybody see the difference? So how are we going to understand this vector? And it turns out there's a really handy little formula for how to think about what that vector is, because after all, being as it is a vector, I can understand any vector by just direction and magnitude. What's the direction that this vector points? Well, nothing to it. There's this little unit vector u here, right? It's just a unit vector pointing in the direction of v. And how far? Oh, okay, I just committed a little semantics crime. I said how far, like it's a distance, and it's not necessarily positive, right? I mean, the projection could be back that way, but plus and minus aside, how far are we going in the u direction? Well, the component, right? So the component tells us, how about this? The component tells us how far, whether plus or minus, in the direction indicated by the unit direction vector u. So direction and magnitude, and bam, we win. There then is the formula for how to compute the projection. Let's see here. There we go. The projection is that formula right there. Is that cool? All right. Now, alternative version of the formula. Pros and cons. But you can take this formula that we just wrote down. You can plug in the fact that the unit vector u, we have a formula of v divided by the magnitude of v, rewrite, move things around, and now here we find ourselves with an alternative formula for the projection. Now this will give you the same exact answer that this will, purple and dark blue, same morally equivalent formulas. right? So you can use either one you want, but I do want to make oh gosh, I didn't want to erase all of that. I do want to make a pitch as to which one I think you should like better. A lot of students are going to be tempted to go with the second formula here. Here's the problem. But here's the good news. Here's why students like this formula at the bottom. V and W were the vectors we were asking about. This is all in terms of V and W. Plug and chug. Right? There's a lot of appeal there. Here's the problem. It's easy to misremember. And I know it is because I see students misremember this formula all the time. Vectors will not always be called V and W. Sometimes it will be the projection of A in the direction of B. Sometimes it will be the projection of B in the direction of A. Which way does it go? And students get confused. It's real easy to mess that up. I see this on exams all the time. Right? This formula up here, it's really hard to mess it up because you can immediately connect this formula with ideas. It's the unit vector. Well, it's the unit vector pointing in the direction of what we're interested in. Of course, it's the direction of what we are here calling V. What else is it? Right? Just look at the picture. This is the only thing that makes sense. Right? And this, scalar factor here, it's the component. Again, easy formula for how to compute components from the previous page. This formula up top in purple connects to ideas and therefore is much more likely that you'll remember this the right way. Whereas this formula down here doesn't really connect to ideas. This is just a rote memorized thing, and some fraction of students will misremember and get this wrong. And that's a problem. Does everybody see the pitch there? And again, keep in mind as well, this class isn't about plug and chug. And even though, yes, this formula at the bottom is arguably better for plug and chug, that's not what we're doing. Right? This formula up top is the one that's better for ideas. It most obviously connects to ideas. You can see the ideas right there in the formula. That's the one I want to hopefully persuade you is the way to think about it. Okay. Last little quickie comment here before we go on, and that is there is some discussion in the book about how you can use vector algebra to do certain proofs in plane geometry. Again, tough choices. Not everything makes the cut for class time. There are perfectly readable, I think pretty straightforward examples in the book. Y'all are already proficient with the idea of vectors and vector addition and stuff like that, vector algebra. Turns out that they're extremely helpful, surprisingly helpful to prove certain facts about geometry. So take a look at those. There's at least one homework exercise that will ask you to prove some result of plane geometry using vector algebra. And if you've read those examples from the book, and if you look at the picture and think strategically, I think you should be able to figure that out. And of course, as always, come to office hours if you have trouble, right? My office hours, the other instructors, et cetera, et cetera. Y'all know the options. Okay. So, on to 1.4. Couple of things to say about cross products and determinants and orders that we're going to talk about first here. But yeah, before I get into it, I want to point out every book is different on how they treat these things. Not in terms of what they tell you necessarily about cross products and determinants, etc. There's a pretty standard list of neat facts to know about these things, but what order they present the ideas. And it turns out that these ideas are not sort of neatly stacked on top of each other with one that's unambiguously first and that everything else is derived, stacked on top like you're building a building. It's just not like that. The various ideas that we're going to need to talk about, they're just kind of all beside each other, and the connections there's countless connections of different sorts. And you can start here and then go there, or you can start here and go in some other zigzag order. It's like a traveling salesman problem kind of a situation. So there's countless different ways that you can walk through these ideas and connect the ideas to each other. The way that I prefer to do it, I think, is my best shot at making a tour of these ideas that's geometrically, intuitively satisfying. That's what I think is most helpful in a situation like this. There is a totally different point of view, which is, hey, which path through these ideas is the most rigorous? That's just not what this class is, right? So I'm going to present these ideas in an order that's significantly different from the order that the book does, because the book's a little bit more focused on rigor. I want to focus more on geometric satisfaction and geometric intuition. So you will notice dramatic differences between how the book talks about this stuff and how I do, and you get to look at both, right? See which one you like better. All right. Okay, so starting with what I'm going to call the idea of the geometric order of a list. Starting with the idea of what is a list. A lot of people mistakenly conflate a list with a set. That's not okay in this situation for a couple of reasons, actually. But the key point, the most important point here, is that these are in order. A list means that one of them is first, and another one is second. And the ordering is part of the list. Okay. So what we have here with A being first. A is first there, right? Now B is second. Like so. And the order being part of the deal, I'm going to say that this order, this list, 1 first, 2 second, A first, B second. I'm going to say it's reasonable to call this a counterclockwise order as per the vectors indicated in this picture here. Right? There was the A vector, there's the B vector. A first, B second has us rotating counterclockwise. You buy it? Seems like a reasonable choice. Now, of course, this same list, were I looking at this being where A was, and if this is where B was, now same list, A first, B second, is now clockwise. Same idea, just different vectors, and so this list has a different geometric interpretation. Everybody happy? Clockwise, counterclockwise. Okay. All right, so it's going to be tempting to say, okay, cool, well then if I have any list of 2 vectors, it's going to be either clockwise or counterclockwise, and that's usually true, but not quite. There are various different annoying cases that don't fit into those scenarios, such as, okay, what if A was 0? Well, again, the 0 vector doesn't have a direction, so clockwise, counterclockwise doesn't make any sense if one of the vectors is 0. Likewise, if the 2 vectors point in the same direction, like I have here, there's no clockwise or counterclockwise. So I'm going to lump all of these other cases into just a big bucket, which you're going to notice happens to be exactly the bucket of linearly dependent cases. They're all linearly dependent, and every linearly dependent case is like this. So all together then, we have kind of 3 different scenarios. All right, now there's some natural, simple properties of these ideas of clockwise and counterclockwise. If I reflect, so for example, I'm going to take a counterclockwise list A and B, and if I reflect those vectors over this purple line, the resulting new vectors form a list that is clockwise. So what I'm going to say here is that counterclockwise and clockwise are mirror images of each other, or they're reflections of each other, however you want to say it. All right. Pretty believable. Let's see here. If you trade positions in the list, if you put A where B was and put B where A was, to result in a new list like so, notice that the original list, A to B, in this case, counterclockwise, the new list, B to A, becomes clockwise. So another way to say this is that anytime you have a list of two vectors, if you switch the positions, that will change the order. What I've drawn here from counterclockwise to clockwise and vice versa, of course, also works. Okay. Last observation I'll make is that the order is independent of rotations, by which I mean if you look at A to B being counterclockwise, for example, right? And now let's suppose I take this entire picture. I'm going to rotate the entire picture by some amount, resulting in now these two vectors, rotation of A and rotation of B. That will still be counterclockwise. So rotating the whole picture doesn't change the order. Yeah? Everybody happy? I mean, geometrically satisfying, right? Okay. All right. The reason I'm talking about clockwise and counterclockwise, well, first of all, it's going to come up in some theorems that we're going to talk about in a second, but also it's a fantastic segue into a much less familiar idea of right-handed order and left-handed order that are also going to come up in some theorems in a couple of minutes, depending on how time goes here. Is there a clock? Let's see here. Is that clock right, by the way? Yes. It's okay. Cool. Good. Okay, I'll trust that clock. So what's the deal with right-hand order and left-hand order? There's a bunch of details. We'll talk about it momentarily. The big picture that I want y'all to have in your minds, though, is that right-handed and left-handed is basically a three-dimensional version of clockwise, counterclockwise. It's going to allow us to talk about a list, talk about a geometric interpretation of the order of the list, and it's going to have morally exactly the same properties that we just got through talking about of clockwise, counterclockwise. Now, before we can get into the details, I do need to do a little hand waving about, let's do this, about what does it mean for a list to be right-handed. Let's look at this first little picture I've got here on the page on the left side. We're looking at the list A, B, C. Keep in mind that means A is first, B is second, C is third. Order matters. Here's the convention. You start with your index finger of your right hand. It has to be your right hand. This is very important. Index finger. You have to point your index finger parallel to your palm. You can't do a move like this. Right? Index finger parallel to your palm. Point that index finger parallel to the first vector. Okay. And now notice you can kind of, I could do it like this. You know what I mean? As long as my index finger is parallel to my palm and in the direction of the first vector. Okay, next. My middle finger. I need to point my middle finger in the direction of the second vector, B. Now, like so, I can't make my middle finger do that. Right? But if I rotate, again, perfectly allowed to rotate my hand sort of around the A vector, you can see now I can point my middle finger in the direction of B. And again, no, hand yoga, right? You can't pull a fast one like this, right? I'm bending the middle finger the way middle fingers want to bend. Yeah? Everybody happy? Okay. Now, the last thing to observe. These first two vectors, A and B, they define a plane. My thumb points on one side of that plane. In this case, what you might call above, but whatever, right? It points on one side of that plane. Notice that the C vector here also points on the same side of that plane. And so because this third vector points on the same side of the plane as my thumb of my right hand, we call this a right-handed order. Now notice if I were to try to do the same thing with my left hand, crash and burn. Here we go. A, index, I'm going to use my left hand. This is not going to work. I'm going to point my index finger in the same direction as A. Now I've got to get my middle finger to point in the direction of B. Notice I've got to do this to get my middle finger to point in the direction of B. Now notice that my thumb doesn't point on the same side that C does. My thumb points down. C is pointing sort of, if you will, on the up side of the plane. I can't make this fit with my left hand. This doesn't work. It's intrinsically right-handed. But this second picture, let's look at the second picture now, is left-handed. A, for first vector, index finger. Second vector, middle finger. Thumb pointing on the same side as the plane as the third vector, C. Is that cool? Okay, so that's the difference between right-handed and left-handed. And just like with clockwise, counterclockwise, there's various neithers. I mean, A could be the 0 vector. B could be the 0 vector. They could both be the 0 vector. C could be in the plane defined by A and B. It could be parallel to B. It could be parallel to A. There's a bazillion annoying misfits, right? But they're all linearly dependent. And so that's what we're going to call the third category, various different cases that are neither right nor left-handed. They're all linearly dependent. Okay, so just like with clockwise, counterclockwise, I now have, for an ordered list, this time 3 vectors in R3, I have 2 primary options that are kind of opposites of each other, and then a third option, which is kind of the collection of various annoying little misfits. Does that make sense? Okay. All right. It's got all the same properties that clockwise, counterclockwise. These are mirror images of each other. Right? A reflection of my right hand is my left hand. Just like clockwise, counterclockwise. Right? If you trade the positions of 2 of the vectors in the list, for example, if I put A where B was, and if I put B where A was, like so, notice what had been ABC, a right-handed list, becomes instead BAC, which is a left-handed list. That make sense? All right. And then lastly, if you rotate the whole picture, then nothing changes. And this is another sort of best seen as a hand waving that if I have a right hand demonstration of ABC as being right-handed, if I rotate all of these vectors some way, well, it's still my right hand. And so having rotated them all, it's still a right-handed list. Let's see here. In fact, what did I do here? Looks like what I did here was, so ABC, like this, and then I rotated to get now RA, RB, and RC, still a right-handed list. So all the same 3 properties that clockwise, counterclockwise has. So I think this is a pretty persuasive pitch. This is a 3D version of clockwise, counterclockwise. Okay, last little quick observation while we're here. There isn't really, this isn't a distinct idea in 2 dimensions, but there's this idea of cycling. When you have a list of 3 things, cycling in this case means taking the first vector and moving it way over to the end to now become the last vector. Right, so ABC becomes BCA. And I claim that cycling will always preserve the order. And roughly speaking, here's the hand-waving demo. This right here. Everybody see what I'm doing? So, like this.
You're switching A with...
I think, let's see here. Maybe, let's see here. So, okay, do I have these? Okay, let's see here. Actually, I'm not sure if my wrist is capable of, let's see here. Okay, so ABC, right? And now let's see here. BCA, I guess, is like this. Yeah, I don't think I can do. Yeah, no, I guess I can. Here we go. There we go. Yeah. that make sense to everybody? So yeah, well, that's right. It's effectively a rotation. That's right. So the point is cycling. If you can do it with your right hand in one order, when you cycle, you can still do it with the same hand, just by kind of twisting your wrist. Does that make sense? So again, this isn't really a distinct idea in 2 dimensions, but it is distinct in 3 dimensions. Okay. So a couple of theorems. Now, again, I think you may have seen these in a linear algebra class, but I think these are really important, so I am going to talk about them a little bit. There's a lot of setup that goes into this first theorem, so bear with me, right? All of this right here isn't even a theorem. That's just setup. The theorem is down below. The theorem is about how these various related objects relate to each other. So before I can tell you that theorem, I have to tell you what these related objects are. So here we go. Suppose we have a list. All right, and keep in mind that means that one of the vectors is first and the other vector is second. I'm going to take that list and I'm going to make a matrix out of that list by taking the first vector and making that my first column, and by taking the second vector and making that my second column. So I just turned a list into a matrix. Okay. If you have a matrix, of course, you have a linear transformation. So given a list that makes a matrix, that makes a linear transformation. And now I'm going to take my linear transformation, and let's see here, my linear transformation. I'm going to ask real quick what happens if I look at the unit square here. And here, let me zoom in so I can see better. There we go. What happens to the unit square? Well, let's take this one edge vector at a time. Let's look at E1 here. E1 being one of the edges of my unit square. What's the image of that standard basis vector? Recall from last week, when a matrix represents a linear transformation, the columns are the images of the standard basis vectors. So an image of a standard basis vector is just the corresponding column. It is therefore the corresponding column, namely the first column, namely it's that first vector in the list. It's A. So the image of the bottom edge of S is A. Likewise, looking at the second edge, the left edge, I guess you might say, that's E2. The image of E2 is the second column, which is that second vector, which is B. And so what's kind of cool about this is that, reminding, we started with a list, we made a matrix, we made a linear transformation, and now we have also made a parallelogram. And it turns out that these things are all very closely related to each other. The list, the matrix, the transformation, and the parallelogram. Strong relationships between them. And now begins the discussion of the actual theorem. But how about this? Before I get into the theorem, does everybody see what these objects are that I'm interested in? And how I've given a list, I create these various objects. Yeah?
What is the S?
It's the unit square. Yeah, so it's the square in the plane where the bottom edge of the square is E1 and then the left edge is E2. Yeah, so in other words, I and J become, yeah, right. Is that cool? Yeah. All right. So first cool fact, by the way, I'm not going to prove this, and you're not responsible for the proof. It's a bit more effort than I think is a good choice for this course. If you take the matrix, compute the absolute value of its determinant, weirdly, that gives you the area of the parallelogram, which is very surprising. think about it just as a quick for example. Computing the absolute value of the determinants, it's four-function arithmetic. You're multiplying and adding stuff. Right? There's not even any division. It's really easy operations. Adding and multiplying, that's it. How would you compute this area, by contrast? And let's take a high school geometry point of view. Well, you'd have to drop a perpendicular and look at the length of the base. Ooh, the length of that base is going to involve a square root. Dropping the perpendicular, that's going to involve some trig. So how can four-function arithmetic, three-function arithmetic, how can that compute something that appears to need square roots and trig? It doesn't look like this could possibly be true, but it is. So anyway, I think it's a real eyebrow raiser. It's a splash of cold water in the face, something like that, right? Very weird result. Okay, next result. Let's see here. Looking at, how are we doing on time? Okay, we're good. So looking at the matrix and thinking not about the absolute value, but the sign of the determinant, by which I mean plus or minus. Right? Whether that determinant is positive or negative, amazingly tells you something about the ordering of the original list. Right, and keep in mind our original list, there's A, there's B, and when you have a list of vectors, it's either clockwise or counterclockwise. And whether it's clockwise or counterclockwise is determined by the sign of the determinant as follows. Let's see here, I got to fit it all on. Whether the determinant is positive, negative, or zero tells you whether the order is counterclockwise, clockwise, or dependent. And again, really surprising, determinant is an algebraic thing, right? It's formulas. Clockwise and counterclockwise are extremely geometric things, right? So again, a real shocker that these two things that seemingly live in different worlds always correspond. Very powerful. Everybody good? All right, let's see the last thing I want to point out. And I'm going to need to zoom in here for a second. Let's talk about this linear transformation here. I've got a picture of. Real quick, what's happening in this linear transformation? And keep in mind, let me just color code that this vector and this vector have images that are that and that. So how would you, geometrically speaking, how would you realize this linear transformation? I think roughly speaking what you would do is you'd take this and you kind of rotate it around, just a little bit of a counterclockwise rotation. You'd kind of shear this way, kind of like that, right? And then maybe you'd have to stretch or something. But there's going to be some pretty simple geometric elements that go into doing what this linear transformation does. That will not include any reflections. Right? There's not going to be any sort of like flip it upside down. Because, for one thing, you can look at the order. Anytime you take, let's see here. There's my finger pointing in a counterclockwise way, right? If I flip it upside down, counterclockwise turns into clockwise. And this is pretty clearly, green to blue is counterclockwise on the left and counterclockwise on the right. There's no flipping. There's no reflecting happening here. That make sense? Okay. On the other hand, let's suppose that I've been looking at a different list of vectors. Let's suppose that this was the A vector and that this was the B vector. And now, notice that what had been green to blue counterclockwise now becomes clockwise. How would we act? What does that tell us about this linear transformation? And I claim no matter how much you stretch no matter how much you rotate, no matter how much you shear, you're never going to make this happen without a reflection. You got to flip it. Does that make sense? Yeah. So linear transformations either do or don't have a reflection inside of them. And that is the last sort of connected dot. If I can get my thing to, here we go. The last neat fact is that just got to erase the garbage here. The sign of the determinant tells us whether the linear transformation does or does not have a reflection hidden inside of it somewhere. And these are the three cases. Positive, negative, 0 for determinant corresponds to either no or yes or, well, if the determinant's 0, this is a singular matrix. It's all squished and stuff, and the question ceases to make sense. And so kind of neither. So anyway, amazing that these things are all connected, and we're out of time, so we will draw the line right here. See y'all on Friday. Have a good rest of your week. Yeah, give me just a second here. I just need to stop the recording.